For the past few years, the whole story in AI has been pretty simple. Bigger is better. We're talking bigger models, bigger data centers, and way, way bigger budgets. But today, we're going to talk about a project that just completely flips that entire script on its head. We are diving into Andrej Karpathy's nanochat. It's a totally radical approach that isn't designed to be the biggest, but to be the absolute smartest and fastest AI training system on the planet.
So just how fast are we talking? Well, get ready for this because this slide is it's mind-blowing. Think back to 2019. Training the original famous GPT-2 model, that would have set you back about $43,000 and taken a full week. Now look at today. nanochat gets to that same level of performance in just over an hour and a half for less than $50. That's not just a little bit better, that's a nearly 1,000 times reduction in cost. It's insane.
And right there, that's the big question, isn't it? That's the central mystery we're going to solve today. How on earth do you get a 99.9% cost reduction in just a handful of years? I'll tell you right now, it's not just about faster computer chips. No, the answer is this brilliant mix of, mathematical elegance, some super specialized tools, and something else entirely unexpected. So the whole idea behind nanochat is built around this concept they call the speed run. If you're a gamer, you know what this is. The goal is to train a model to the exact same level as OpenAI's original 1.5 billion parameter GPT-2, but you have to do it as fast as humanly possible. It's a flat-out race against the clock, using today's cutting-edge tech to chase down a historic benchmark. But here's the thing. This race has a very strict referee. This isn't just about being fast. You have to be good. To win the speedrun, your model has to beat the original GPT-2's core score. And this is no simple test. It's a really tough, normalized benchmark that measures language skills across 22 different datasets. The magic number to beat is 0.2565. If you can get past that, you've officially won. Okay, so how do you even begin to get that kind of speed? Well, our first big clue isn't about throwing more computers at the problem. It's about starting with a much, much more elegant design. Instead of a human engineer sitting there tweaking dozens of settings by hand, the nanochat philosophy is to just eliminate all that guesswork with pure math. And this is what that mathematical elegance looks like in practice. It's called the depth-derived scaling framework. Just think of it like this. You have one single master complexity dial. It's just one parameter called depth. You set that one number, and bam, the framework automatically calculates every other single dimension of the model to be perfectly optimal for the computer it's running on. No more guessing, just a clean, perfect formula. And here you can see exactly how that plays out. Just by changing that one little depth number, you can instantly create a whole mini-series of different models. If you look at the table, as you turn that dial from 12 up to 26, you get this whole family of models, each one bigger and more powerful. Now, for this GPT-2 speedrun, the team was focused right on the D=24 and D=26 models. Those are the ones right in that sweet spot to match the original's 1.5 billion parameters.
Okay, so we've got a smarter blueprint for the model, but you also need a smarter engine to actually build the thing, right? And that brings us to our second clue in this 1000x mystery, a super specialized dual optimizer engine that trains the model with just unbelievable efficiency.
See, here's the key thing to understand. Not all the parts inside an AI model are built the same. You've got some simple one-dimensional lists of numbers, but then you've got these other massive two-dimensional matrices. So nanochat uses a right tool for the right job approach. It uses the standard Atom W optimizer for the simple stuff, and then it brings out the big guns, a specialized optimizer called muon for those huge, complex weight matrices. It's kind of like a mechanic using a tiny screwdriver for delicate electronics and a giant impact wrench for the big lug nuts. Now, this muon optimizer, this is where things get really, really cool. It's not just blindly pushing numbers around. In simple terms, it first figures out the best direction to learn, but then it does this critical step called orthogonalization. And this is the secret sauce. It mathematically forces all the model's internal pathways to be as different from each other as possible. This maximizes how much information the network can actually hold. It's literally reshaping the model's brain for peak learning. And this quote just perfectly captures the why behind all of that. By keeping those updates geometrically orthogonal, you basically stop different brain cells, or neurons, from learning the exact same thing. It's like the ultimate defense against wasted effort. Every single parameter is forced to pull its own weight, which maximizes the model's total learning power. Absolutely nothing is wasted. So we've got a smart architecture and a powerful engine. But even that doesn't quite get us to a 1000x leap. The final clue. Well, the final clue is the most surprising, almost science fiction part of this whole story. It turns out some of the most important optimizations weren't designed by people at all.
What on earth does that mean? Well, think about it. Because training a nanochat model is so unbelievably fast and cheap, we're talking just minutes for the smaller versions, it accidentally created the perfect environment for other AIs to start running their own experiments. It became like a computational petri dish where you could just let autonomous AI agents loose and see if they could improve the code themselves.
And this is the loop they set up. It ran over and over 24/7. An AI agent would literally rewrite a chunk of the nanochat code. Then it would kick off a training run with its new code, but with a super strict 5-minute time limit. If that new code resulted in better performance per second, success, the change gets saved. If not, the code gets thrown out, and the AI tries a totally different idea. This process just ran relentlessly, conducting thousands of experiments overnight, a pace no human team could ever dream of matching. And what came out of all this relentless, automated research? Real, powerful, and frankly, some pretty creative new architectural ideas. The AI agents invented things like the smear module. It cleverly feeds cheap, basic word pairing information into the model's earlier layers, which frees up the really heavy-duty parts of the AI for more complex thinking later on. They also came up with the back-out connection, which basically acts like a noise filter, subtracting out static from the final layers to make the output sharper. And these aren't small tweaks. These two AI-discovered ideas alone were responsible for shaving another 19% off the world record training time. All right, so let's put all the pieces together and solve the mystery. The 1000x leap wasn't just one magic bullet. It was this powerful combination of an elegant architecture, a hyper-efficient training engine, and this incredible autonomous research loop. What they've built isn't just a model, it's a complete factory for discovering how to build better AI way, way faster.
And this AI factory is part of a much bigger trend that's happening. What this chart is showing us is that the cost to train an AI to the level of GPT-2 is going down by about 60% every single year. So every year, the price drops to just 40% of what it was the year before. And the most important part? This is being driven more by smart algorithms and software, like everything we just talked about, than by just raw hardware getting faster. Powerful AI is getting cheaper and more accessible every single year.
And really, that's the final, most important takeaway here. NanoChat is so much bigger than just a cheap way to build a chatbot. Its true significance is its new role as a platform, an engine that actually allows AI to start improving itself at scale. It's a fast, cheap, and incredibly effective testbed for accelerating the very future of AI research.
Which, of course, leaves us with one last, really big thought. For decades, the progress of AI has been limited by the speed of human researchers. But if we now have factories where AI can relentlessly and efficiently speed up its own discovery, what does that mean for the next 5 years? What comes next?